Hello there, everybody, and welcome back to Ohio. In the previous episode, we were able to put down a little bit of water production. Not enough to really survive, but enough to sort of start the process of thriving, maybe, potentially. I don't want to get too ahead of myself here. Let me grab my atmospherics tablet. We can look at this. We got 366 pascals. That's right, without the K. Of 1,521 degrees Celsius water. Well, steam, really. It's 0.015 moles. We got a long way to go, buddy. Thankfully, we do have some food, at least. Our potatoes have come in, and we can now harvest the seeds from them, which is huge. I do also have some news. The comment section did some amazing detective work and has figured out that in order for us to survive on potato plants alone, we need 9 of them running. 9 plants will produce enough oxygen and convert enough CO2 for us to keep breathing. So basically, if we did nothing else, we could just kind of survive at this point. We could eat the potatoes and we could breathe the gas that they produce. I think we're just shy. What are we at? 6, 7, 9. No, never mind. This is exactly the number we need to maintain our own breath. However, they are going to consume water. And there we go, there's the problem. We have no way of getting more water, as we discussed last time. That is going to have to change soon. Now, in order to then produce the water, we have to burn some of the oxygen these plants make with the hydrogen in the atmosphere, which means that we're actually now in a deficit. We need more plants to make up the oxygen that we have to burn in order to get these guys going. Apparently, according to the comments section, this balances out at around 24 potato plants. 24 potato plants should, and the keyword here is should, be just the right amount to get us going on that front. Hopefully that remains true. We're going to eat our potato. We are going to want to get a fridge today. These are going to start spoiling. 4 hours. We got time. Now, in between episodes, I have gained new knowledge. I have become more powerful than I ever thought was possible. I now kind of understand how to code the IC-10 chips. Chat and I had a long, arduous stream where we worked through that one together. We settled our differences and we decided to collaborate for once. And let me tell you, it's been powerful. Consulting the holy texts, we will first use alias to define... We will use alias to define human-readable values to devices set to the pins on the IC chip. Okay, then we will use define to not have to reference the hash code of things all the time. We can just type a name for it. I now, for the most part, understand how to at least put together basic systems, right? Things to automate things like moving gases around at certain trigger points. And to do that, we're going to use these. This is a laptop, which I printed on the electronics printer. You can also use the stationary computer, but I decided to just go straight for this one because we have the tier 2 printer. You'll need to take the IC editor motherboard, and you'll need to put that inside your laptop. It'll need a battery over here. And then you're going to need this thing, an integrated circuit. The integrated circuit is that little chip over there on the right-hand side. You chuck your laptop on the floor, and you can edit, and you can type all sorts of things, like this. There you go. All right, now that's not code, not yet anyway, because we're actually going to have to do a couple of other things before we get into the coding. I just wanted to show you that I have gone ahead and gotten myself a laptop. We're going to stash that over there for now. And what do I actually want to work on first? Well, I think the most important thing we can do is to cool down that water. And in order to do that, we are going to need a heat exchanger. Okay, so the heat exchanger is pretty dope. What this thing does is it exchanges heat between a gas and a liquid, or a gas and a gas, or a liquid and a liquid. It's just a much more efficient way of transferring heat between your systems than trying to do it all with your... Because you could build like a room with a bunch of radiators and pump the gas in and then radiate it out. This just does it for you in one block. It's just a lot more simple on the calculations and on the brain. Now, I also am going to need some other things. We're basically going to want to take night gas. We're going to want to exchange the heat with our water network, and I think I'm just going to need some more liquid pipes to do that. And that should bring the temperature down in our liquid pipe from, what is it, like 1,000 degrees, 1,500 Celsius to like, I don't know, 100, which is it's a pretty big reduction just on its own. And we've already got the night gas, so we might as well use it. And something else I want to make is an IC housing. This is the little chip housing. I think it's the IC... this one right there. There we go. I need steel and copper. Okay, so heading around back here, we can do it, I think, up here. We want to exchange the heat that is currently in this liquid pipe with what is over here. Or actually, maybe, now that I think about it, maybe we want to exchange the heat between that steam pipe, so before it goes to liquid. Yeah, that makes more sense, right? So we can put the heat exchanger over there, so we tap into our night gas and that one. That works for me. And the nice thing about using a heat exchanger to do this is it requires, like, no power at all. Alright, so I'm actually going to want a gas-to-gas heat exchanger in that case. Okay, heat exchanger over there. It doesn't even need to be welded. Awesome. So that was output... Aha, it's labeled. It's labeled. Okay, so input and output 2. So basically, we're just going to feed these into each other. Okay, so that's connecting our night gas to this system. And now we want to connect these super duper hot steam bits to our system as well. And I think I'm just going to do something like this. And we will definitely need to come and color code this blue. So we remember it is for the welter. So right now, the temperature is plummeting. Look at that. Absolutely plummeting. This is increasing rapidly. That is our air conditioning pipe. So it's not ideal. We are going to stop being able to air condition. But we have dropped the temperature in our water pipe by like a bajillion degrees Celsius. Okay, great. I mean, the water in this pipe is still super duper hot. That's okay. But this one is coming down, and these will equalize, right? So they'll equalize at around, looks like 160. Yeah, 160. 170. 170. Okay, they'll equalize at about 170, and that, just with that alone, we have shaved off 90% of the heat. We're still going to have to do some other shenanigans to cool it properly, but that's a good start. And I think the other cooling shenanigans will have to happen sort of over here. We're going to use an evaporation chamber, like Balin showed us, alongside some liquefied pollutant, which I need to get started on capturing. We're going to need a lot of pipe utility kits in order to make that happen. So let's go ahead and just start making them. We're going to just need a ton of atmospherics equipment. Okay, I need 12 pipe utility gas kits so that we can make a bunch of expansion chambers. I'm going to need an insulated liquid tank to store the liquid pollutant, a ton of insulated pipes of all descriptions. Oh, a kitten. She's got the zoomies. Okay, the beast has been contained. We're so back. Let me just feed this some more material. How many have we got so far? 8, 9. Perfect. One more. Then I want you to make me an insulated liquid tank. This is going to be for the liquid pollutant. Okay, then I'm going to need just like a disgusting number of valves. Actually, I want an active vent first. And you can make me some frames. I think we're going to need a lot more of these. We need to be able to pull gas in. We've actually already got vents up there. I can just repurpose that system. Okay, that'll work. And we'll use the chips here to make it happen. Okay. We could just go... Oh, you know what? I need some valves. I need just a ton of pipe valves because we need to be able to do expansion and compression and all that sort of good stuff. And then give me a couple pressure regulators so that we can purge. Okay, and that's all we actually need for now. So what we can start doing is working on our code. So I'm going to chuck this down over here. If you'd like to see how I learned how to do this, you can check out the live stream. It was linked in the previous episode, and if we remember to, we'll link it in this one as well. But basically, I'm going to walk through the very simple parts of this, and if you don't understand, don't worry. It's not that critical. But if you would like to learn how to code IC10, I can try and put together some like super beginner tutorials, because I'm coming at it from the mindset of someone who's never done this before. Basically, let me just quickly describe what we're going to be looking at here. Alright, so if I put down this chip holder, you'll see that the housing has 6 pins, labeled D0 to D5. You can connect external devices to it using that. You can also talk to any device, I can talk to every single vent on the connected data network with that comes in from the cables. Or if I want to talk to a specific vent or sensor or tank, I can put them on these pins. Okay, but how do we talk to the different pins in the code? It's pretty straightforward. Turns out you can just type the name of the pin, D0. That would talk to whatever's on D0, but it's kind of hard to keep that in your head, so you can also give it a human-readable name using the command alias. alias will assign a human readable string, also known as text, to a specific pin. So I'm going to call my first pin sensor, and we'll just remember to attach the gas sensor to it. I'm going to call my second pin, I'm going to call that the tank. There we go. And we're going to put that on D1. So D0, sensor, D1, tank. We just got to remember to attach that. Then I want to talk to every single active vent on the data network that I'm going to plug this thing into, because those are going to be the ones that are going to push and pull all my gas. And to do that, I'm going to define, it's a different command. I'm going to define a vent as being any item. If I go to active vent, we're going to define a vent as being any item that has this hash number. Every built active vent in the game, make sure you don't select the vent kit. I made that mistake before. Every built vent on the data network will have this hash number. And so basically any item on the data network that this chip is connected to with this number will now be spoken to whenever we type vent. Okay, cool. Also, you can pause the game up here in the top right if you didn't know. It's just a good way to save some resources while you're working on this stuff. So I can actually go ahead, confirm this, and export it. And you'll see our chip now has 55 bytes of data in it. If I put this back in, I could drop this, I could edit, I could lose this. Oh no, I've lost all my code, my laptop's on fire and it's all disappeared. No worries, I just get the chip back, hit import, and there we go, there's our code. This code doesn't do anything except tell the pins what they're called. Now, we need to actually do something with this information. So I'm going to start a new thread, right? A new function inside the programming. You can call this whatever you want. For simplicity, I'm just going to call it start. All right, so we're going to start our process. But now I don't want the code to engage right away because I'm worried that it's going to skip some functions. It's going to move too quickly for the game to keep up. Oh God, please pause. So I'm going to type yield. Yield just literally, as the tooltip says, makes the code wait for one game tick. It's like a 60th of a second. I actually don't know what the tick rate is. We're going to assume it's a 60th of a second. It just lets the code pause, take a breather, relax for a little bit, lets it come back to us. All right, now we're going to want to do something with the information that's stored on these pins. So we're going to type L to load information, right? We are going to load into register 0, which is kind of like a floating variable. A register, you can think of there's 15 of them on every chip, one for each of those little metal pins on the side. And what the registers do is kind of act like a bit of memory where you can store information and you can take it out and you can overwrite it, but it will all happen inside the loop that we create over here. We could load into the memory outside of the loop, but then it won't happen again. So we want to do it inside of our function so that every time this function runs, we load this data back in here again. There's 16 registers named R0 to R16, R15, and you can call these whatever you want. We can also alias our registers, by the way. So we could say alias temp, and we could alias that to R0. So every time we wanted to talk about the temperature, we could put that there instead. But I'm just going to use the numbers because I'm going to be overwriting the register just to save on memory. It's not super critical. My chat told me it was best practice. Also, you know what? We can add some comments here. Okay, there we go. So very helpful comments to help you keep up. Now, we are going to load into register 0, memory point number 1. We are going to load what? Well, we're going to have to choose a location to load from. We're going to want to load from our sensor. And we're going to load the temperature. If we go to the gas sensor in our F1 menu, get gas sensor, if we can see the different things we can read from it, we're going to want to read the temperature. You can always click on that to see exactly what it's talking about, but it's not overly complex. Remember to pause the game every time you leave that. And we're going to load in the temperature. So what's happening right now is whatever the sensor is reading is going to be loaded into R0. However, that's going to be in Kelvin, which isn't super helpful to us, so I want to convert that to Celsius. The easiest way to do that is just to subtract 273. It's not precise, I think we're actually losing a decimal point, but that's okay. So we're going to subtract into R0, and 273. Now, this is where MIPS loses me a little bit, because it doesn't flow from left to right like a human would read it. It drives me a little bit insane, to be honest. I would have put this one at the end, because what's happening is we are saying, okay, I want you to now subtract whatever the value in R0 is minus 273. Then take the result of this equation, these last two numbers, and put it over here. So we're going to read the R0 value that we got from here, the temperature. We're going to minus 273 from it, and then we're going to overwrite this information over here. We could call this R1, and then work with a different variable all the way down, but I'm going to get into the good coding practice of overwriting my R's and my zeros from the get-go. So now, our R0 is no longer whatever the temperature reading was. Our R0 is now the value of whatever the temperature was minus 273, basically the Celsius. So, what do we want to do with that? Well, we want to check if the temperature outside is less than 130 C, we want to do something with it. We want to pull in the night gas. So we're going to say set less than or equal to, check R0, 130. Now, what does this bit of code do? Well, as you can see, the register will equal 1 if A, which is R0, is less than or equal to B. This will be 1. If it is not true, if that function is not true, if the value we got here from this temperature is is more than 130, this thing here will now be overwritten with a 0. If it is less than 130, this thing will be overwritten with the 1. Why do we want to do that? Well, we can use a 1 or a 0 to turn on an active vent, just like we did with the logic chips. So what we would do here is say set batch, right? So we're going to set a state for everything of this type, so same as a batch writer. We're going to want to talk to our vent. So instead of having to put the device hash, we can just write vent because we defined it up here. And we're going to want to say turn yourself on or off. That's our logic type. And you're going to set yourself to whatever is stored in R0. Then, in order to make this thing loop, we're going to say jump back to the start. We could call this quite literally anything. We could call this night gas if we wanted to, right? And then we're going to jump back to the start of night gas. But I'm just going to leave it as start for now. All right, lovely. So that is actual functional code. This will turn on the vent if and when the temperature outside drops below 130. But we also want to make sure our tank doesn't blow up, right? Our pressure tank. So what we're going to do is we're going to do another bit of coding here. So let's put a comment in. This is going to be that's going to be our night gas temperature check. And then we're also going to want to do a new one, which is going to be our gas tank pressure check. And we're going to do something very similar. Here we're going to load into a new register. We'll call this one R1. We don't want to overwrite whatever's going on here. We're going to load into R1 the tank pressure logic type. There we go. So now we're going to load up the tank pressure. Once we have the tank pressure in hand, what do we want to do? If the pressure in R1 is less than 5,000 megapascals, go ahead and set the R1, overwrite the value here with the 1. If it's more than that, override it with a 0. Then we're going to want to turn the vent on. But now, here's a problem. We can't turn the vent on with R0 because then it's not talking to this variable. So we're going to use an AND gate. And this is just like the AND gate we had to use with the logic chips, right? So we want to check if R1 and R0 are both true. If they're both equal to 1, then turn the vents on. So we're going to say AND. I'm going to make a new variable, which will be R2, and that's going to check are R0 and R1 equal to one another. If they are, then R2 will be set to 1. If not, then R2 will be set to 0, and we're going to set the vent on value to whatever R2 is. Basically, if either of these checks fail, the vents will be set off. If both of them are true, the vents will be set on. This right here is some functional code. And we're just going to say here, that's our loop. Jumping back to the start is to make this whole thing loop. And that's it. It's really not that tough. I understand this is a lot of gibberish coming at you. If you would like to see designed bespoke tutorials about how to do this, going from first principles, explaining its way up, I will do my best to create them. It'll have to be in collaboration with the Discord community so that I don't screw it up. But that is something I would be down to try and plan out and design as a mini sub-series. Maybe not as part of this one. As part of this series from now on, we're just going to start coding stuff. And I'll be asking for support. But that is, if that's something you want to see, let me know. I'm not going to explain it every time because it's going to start really eating into these episodes. Okay, confirm. Let's go ahead and export that information. We're going to pick up this chip right over here. And we're going to go outside and we're going to get ourselves some gosh darn logic refining. At least that's what we would do if it wasn't the middle of the damn day. You know what we can do quickly? Let's go get some water while we're waiting for that sun to set. Make myself another baked potato. And we're at 2 liters. That's scary. Alright, so all of this nightmare over here is going to get compressed down quite a bit shortly. But we're going to have to do some other shenanigans first. I'm going to pull up my... where are we going to put this? You know what? Maybe we pick up the old logic first. We can always recycle it at some point. Okay, give me the... let's just turn off that batch writer first. Let's pick up the compare units. All this work for naught. Okay, cool. So that little loop is set back up. Now, let's just cut into it again. We're going to want to set up our little chip. And we're going to put that right over here for simplicity and ease. I really hope this thing isn't damaged by storms. I actually have no idea. So let's put down our logic housing. We're going to put that right over there. And we're going to stick our chip into it. Awesome. We should now quickly set these pins. So this has got to go to the gas sensor. And you've got to go to the tank. Turn you on. And it's turning them on. Excellent. And it's going to turn it on until this hits the pressure limit. Perfect. Alright, now we also are going to want to add another feature, which is going to vacuum this tank out when the temperature in the tank system is too high. That's going to be the next thing we work on here. I'm just going to move this logic back indoors, and we're going to continue building out the other parts of this system. Okay, here we are outside. It is now time to figure out what we're going to be doing with these night tanks. Basically, we want to push so much gas into this space so that we can condense down the liquid pollutant and capture it for later, right? We're going to use that liquid pollutant to cool down our base. We're going to use some black magic voodoo, also known as thermal dynamics, and that's going to be how we manage to magic our way through this heat crisis we're currently facing. So taking a quick look at the chart for pollutant here, specifically liquid pollutant, we will see that pollutant will liquefy at 126C only if it is at 5.364 kilopascals of pressure. So basically, we're going to want to make it so that this network right here, which we have been using anyway, is able to support that kind of pressure and also allow the pollutant to condense down into a liquid pipe that we can extract from. So I think what we're going to do, that's going to be our water pipe running over there. I don't love how we've got crisscrossing networks of all different sorts and sizes, but yeah, c'est la vie at this point. Let's go ahead and set up an expansion valve system. And what we're going to do with that is we are going to allow the liquid that we pressurize into this tank, which we aren't doing yet, right? Make no mistake, we're not doing that yet. We're going to want to allow that to condense down into liquid pollutants. So let's go ahead and build a sort of tank over here. I think I'm going to want to do that. Yeah. And we're going to want to connect these up. Okay, lovely. We're also going to want to be able to get rid of the excess here. In fact, we might even be able to get away with doing like a bit of a passive gas expulsion. I'm just going to need to go get more insulated pipes. Maybe we don't have to set up specific logic to deal with the hot gas. Maybe we can just kind of cycle the gas through every night. Yeah, maybe that's easier. And then over time, it'll just sort of naturally return to 126C. I think I know how I can do that. And it's going to involve a lot of these. Alright, so the first thing we're going to need to do is connect this up to our gas network so that any pollutant that does manage to liquefy, we can immediately start capturing in that other tank. Okay, lovely, and turn those valves on. Now, right now, nothing's liquefying because it's too hot. We need to start cooling it down. What we can do to help with that is to add some more volume. And that's what all of these were for. That was just to basically give us even more space in here. Perfect. I needed 12. Okay, my bad. We should start pulling in gas. But it's too hot now. Dang. Okay, but we can also set off a relief valve, and maybe we do that right over here. And this all comes from Balin's design, so please don't give me credit for it. I have studied the sacred texts, and I've begun to understand. We're going to want a one-way gas valve so that hot air can't get back in. We're going to put that over here. We're then going to put another one over there. We're going to add another pipe on top of that. We're going to add a cross joint here. In fact, you know what? This can be a cross joint too. And this one should be a cross joint, not that one. And the reason I'm doing this, we're going to put a pipe flue valve on top, sort of like a pipe cowling on top so that we can let gas out. And what this will do is it will let gas out of this system slowly. These pressure valves restrict the flow quite a bit. And so what I'm hoping will end up happening is that we'll be able to pull gas in at night faster than this can let it out. And that's going to let us build up pressure, build up that hot pollutant, which will then leak out into this tank to be stored and used later. That's the dream anyway. We'll see how that pays out. Now, the reason I put these little valves here is since we're going to be building up pressure inside those spaces, we might as well get some more condensation out of it, right? I mean, literally, why not? So let's just do something like this. We'll turn both of those on. Oh, so actually that one's a bit redundant. Now, you know what? This can be a T-junction. If we can get some pollutant out of that space, let's get some pollutant out of that space. And we'll add another condensation valve up there. We'll turn that on, and then we just need to link this all up with the liquid pipes. So basically what's happening now is if there ever comes a time where there is liquid pollutant in any of these pipes, it's all going to get slurped down towards the tank and stored. Okay, cool. That is going to work. I think this one's a bit redundant. In fact, I am so limited on resources, I think we'll actually just pick that back up. Okay, lovely. So that's going to work. Now, we actually don't care about the pressure in this tank. This is the tank pressure we care about. We don't want this one to blow up. This is never going to hit 5 megapascals because this stuff is just going to vent itself. We basically don't care about this gas because we'll just collect more every night. We're going to stop using it for cooling soon. So I actually want to make this the tank we talk to, and this is the tank we read pressure from, not the gas tank we had over here. So let's peel this off. Oh, we're also going to want to remove that liquid escape valve. We definitely do not want the liquid escaping anymore. Work quickly, work quickly. Liquid pollutant tank. There we go. Set the D1 to be that tank. There we go. Read that pressure. Pull this thing up. If we get liquefaction in this pipe, we now want it to drain into there. Okay, dope. Get inside before you die. You know what? This could just go on here. Don't think we'll need it, but why not? Okay. I'm gonna die. I think I'm dead. Yeah, my lungs are cooked. Wait, eat the pill. I'm alive. Oh, okay, we can't do that again. I even had an extra tank on me, man. I'm so dumb. Oh, we nearly died. I basically set my lungs on fire there for a little second. That was a little too spicy, even for me. Okay. This is the last time we can drink this water before we perish. But we now have automated night gas capture, and it's happening via logic circuits for a change, which is super duper cool. But there you go, everybody. That is all the time we have for today for Stationeers. Thank you all so much for watching, for joining me on this very near-death experience. It's been super duper cool to finally get into coding. I can't believe the day has finally arrived with me, yes me, largely unemployed, has begun to comprehend assembly, like computer machine code. That's crazy, man. Like, this is not a high-level coding system at all, and I have no STEM background whatsoever. Anyway, it's been an absolute pleasure staring at these ones and zeros with you, inside the simulated ones and zeros, on top of the ones and zeros simulated by my graphics card to put things on the display, and it's all just simulacra all the way down. Heidegger was right. Thank you all so much for being here. I will see you all in the next one. Cheers. You made it to the end of the video. Congratulations and thank you. That puts you in the top 3% of viewers. Here's another video that YouTube thinks you're going to like, and here is a list of all the patron and channel member names. If you don't see yours on there, you can find a link down in the description where you can sign up and support this content directly. If your name is on there, well, you probably already know that, huh? So, what are you still doing here?